Hello, and welcome to Construction Tech, presented by House Accelerator, a catalyst of zero-carbon building. We're happy you're here. We welcome all comers to our exploration of how to slash the greenhouse gas emissions of our buildings and make them more resilient to the extreme temperatures, wild weather, and grid insecurity caused by climate change. With our co-hosts, Kevin Brennan, Shannon Pendleton, Sean St. Amour, and Mark Willey, we produce this weekly series to dive into the details of Passive House construction practice, with a technical focus on technique and technology in the field. New to all of this, please visit the Passive House 101 section of our website to get started. With that, please enjoy Construction Tech and pose your questions in chat for the discussion session following the presentation. Thank you. All right, we're very excited to have you all here tonight and to have Allison Bailes presenting duct design for low static air handlers at tonight's Construction Tech. So with that, co-host, please take it away. Thank you.
Excellent. I'm up first. I'm Kevin Brennan. I'm from New York City. I own and operate Brennan Insulation and Air Tightness here. I have been in passive house and building science for many years, and I have known of the work of Dr. Bailes for many years. We've run paths at such events known as Building Science Summer Camp and some of the affordable comforts throughout the world. I've been inspired by his work in residential construction and his focus on HVAC. I'm sure you guys are going to be inspired by his work. Myself, I'll be taking notes because I need to put one of these low pressure air handlers in my attic because the shoemaker doesn't have a perfect duct system and needs to put it in his own house. So I'm ready to be inspired, and I'm going to kick it off to my fellow co-host, Mark.
Thank you, Kevin. So my name is Mark Willey, and one of my favorite things, what happens when Allison posts things is the comments and questions that arise on social media are intense. And everyone is sharing what they learned and questioning what they don't know. And we invite you to do the same tonight. When you hear something in the presentation, put in the comments that it blows your mind or you agree with it or more of this. And if you have questions, throw up a big old Q and add that question, and you'll be called upon later to ask it live. So I am saying hello to Sean because he's joining us from Toronto. Apparently there's a sport where people put on skates and use little black things to chase. And so that's where he's at. And I'm passing it over to Miss Shannon.
Thank you, Mark. Thanks, Kevin. Thanks, Zach. And Sean, I hope your team wins. I hear there's a puck involved. I've never seen it, but I hear it's there. And thank you to everyone else for coming tonight. We've got some great new faces. We hope you enjoyed tonight's show. We've got an excellent guest. Even if you've never built anything bigger than a bookcase, tonight's guest is going to show you why there's hope and bring us the big picture. He spends his day job creating markets, spreading the word, expanding networks, and doing what he loves. If you connect and follow with him on LinkedIn, he'll even remind you to change the filters on your mini split. His upcoming book in progress, A House Needs to Breathe, or Does It, is slated to come out next spring. So please join me in welcoming our esteemed guest, Mr. Allison Bailes III, PhD. Welcome, Dr. Bailes.
Oh, thank you. Thank you. All right. This is great. Wow, this looks like a lot of people here, and I am going to talk about some fun stuff that I have direct experience with. My company, Energy Vanguard, is a third-party HVAC design company, among other things. And so we do a lot of design for other people, but we've also designed the HVAC systems for our office and for my house. And so I'll show you those systems tonight and how they work. So let me get this set up for sharing.
While you do that, Allison, I'm going to drop your LinkedIn into the chat. So please connect with Allison there. And I'll
Yes.
put in also the Energy Vanguard website that you just mentioned.
Yeah, and I've got that in the slideshow too. But yeah, LinkedIn is where I'm most active on social media. I hate Facebook. We do have a company Facebook page, reluctantly. I'm active on Twitter somewhat, but LinkedIn is the place where I'm most active and where I get the most engagement. So yeah, what Mark was talking about is mostly on LinkedIn. And it's not, I don't know if I've posted about changing your filters, Shannon, but I definitely, the other day I posted about flushing your water heater because I did that a couple of weeks ago. All right.
That's
Can everybody?
right. Thank you for that reminder.
Yeah. Can everybody see this? The title slide?
Looks great.
Okay. All right. So we're going to talk about duct design for low static air handlers. Now, a lot of people are scared of low static air handlers, but before we get into that, anybody who is here tonight and doesn't know me and saw my name maybe Googled Allison and was wondering what I look like. This is what you get if you Google the name Allison. I'm not any of those people though. Although I am in Who's Who of American Women. And one time somebody asked me if it's because I used to be a woman, and no, it's not. Not that there's anything wrong with that, but no. So anyway, let's talk about ductwork first. Before we get into low static air handlers, let's talk about ductwork. And you know, why even talk about duct design and low static air handlers? Because I mean, you know, ducts. I mean, we know how to do ducts, right? Look at this system. Flex duct does everything we need it to do. So why should we bother with anything else? That's just a beautiful system right there. It won't work with crap, but it looks nice, right? With flex duct, you can turn the air on a dime. And if you don't have a dime, you can turn it on a nickel. It's really good at doing stuff that hard pipe can't do, like squeezing in tight places. You know, hard pipe can't do that. Yeah, sometimes there's problems with flex duct, but look, let me show you the advantage of flex duct, even a situation like this, because, you know, yeah, it's been torn down by some critters in the crawl space, but you see that wire? That's the helical wire that keeps the shape of the flex duct, and it's still attached to the boot, and that's guiding the air to the boot. That's the path of least resistance right there. That's how the air gets to the boot. Another advantage of flex duct is you can make the air really quiet by cutting the airflow down to next to nothing by putting in extra length. And you don't have to take extra duct back with you on the truck when you're done installing. In the South, dehumidification is a big thing. And one way to do dehumidification is to cool the air down, make it really, really cold, and then reheat it, the reheat system. This is a reheat system in Charleston, South Carolina. Very inexpensive reheat right here. You just staple the flex duct up right under the roof deck. Lots of reheat there. Of course, we want ducts inside the enclosure, and everybody thinks you have to use hard pipe for that, but hey, you can do it with flex duct too. Plumbers love flex duct, as does everybody. You know what plumbers call flex duct? Knee pads. I heard you all laughing in my head. So the, you know, when you design a duct system, it has to be absolutely clear which way the air is going, where it's coming from, where it's going to. And if anybody can figure this out, please let me know. But it's always easy to retrofit it. If it doesn't work, you can just chop it off and tape it up with duct tape. And you can use things like downspout from your gutter system. You can use a piece of cord lying around. You can use trash bags, you know, boots and suspenders here, double tie it on there. Hard pipe, of course, some people think is the answer. This was a hard pipe system I took apart. Well, I didn't take it apart. I took the insulation off. It fell apart by itself. The insulation was what was holding it together. Here's a hard pipe system. Again, very confusing. I think the reason for this is somebody didn't want to take the stuff back to the shop with them, or they wanted to use up a bunch of fittings. I'm not sure, but this makes no sense at all. So if your brain is hurting, mine is too. And you know, looking at that brain kind of reminds me of flex duct actually. But let's calm down. This will make everybody feel better. A monkey petting a bird. I mean, look how cute that thing is. Look at those little fingers. Oh man. Let's leave it there for about 5 minutes. Take a deep breath. Okay, let's go. All right, let's get into some of the real stuff here. So one of the things about low static air handlers that a lot of people believe, and this is common. I've had a lot of people say this, you can't put too much ductwork on a low static air handler because it just doesn't have the oomph to push that air through a long duct system. And that's not true. Here's the duct plan for my house. There are two low static duct systems in the attic. So here's one for the bedroom side of the house, and that's a fair amount of duct work over there. One return, and then a bunch of supplies with a trunk line. The part of the house, the main part of the house over here has a bigger air handler, same rated for same static pressure. It's a Mitsubishi SEZ unit, and rated for 0.2 inch of water column static pressure, which is pretty low. Standard air handlers are rated for 0.5 or 0.6. So 0.2 is really low, which means you have to have a really good duct system to make it work. And some people would look at this and say, oh, there's no way all that duct work on a low static air handler is ever going to work. And they're wrong, because it does work. This is in my house. I know it works because I've lived with it for 2 years now, and it's great. So why does it work? That's the question. We want to know. Oops, let me do this. We need to know why it works. And the reason it works is that I am a juggler, and duct design is really nothing but juggling. You've got some different things to juggle to make it work. The first thing is pressure. Pressure is only one factor in the equation. And when people say you can't put too much duct work on a low static air handler, they're thinking that pressure is the only thing that matters. But pressure is not the only thing that matters. Pressure comes from the blower, and HVAC guys are usually they're used to working with big blowers that have a lot of pressure, a lot of force, and can move the air with higher pressure. But in passive house and high performance homes, there are these things called variable capacity mini split heat pumps. And yes, you can get them with higher static pressure, and we do a fair number of our designs with the higher static versions of these, because we don't always have control over what the contractors and the installers are going to do with the duct system. So we often will go with the higher static units, but the low static units are great. They use less energy. You just have to make sure the ducts are going to work with them. So in residential systems, it starts with the blower. You pick a blower, and then you design your duct system around that. That's the opposite of commercial systems. In a commercial system, you design your duct system, and then you figure out what blower you need to go with it. But in residential, you pick the blower first and then design the duct system. So the juggling happens by looking at the other factors. And one of those is the airflow rate. The blower has a pressure rating, and for each pressure, there will be an airflow, and that airflow and the pressure go together. So the CFM and the static pressure go together. They're determined by the air handler. But you also put a duct system on there, unless it's a ductless unit. And there's a couple of things that affect your ability to move the air, the amount of air that you want to the places where you want it. One is the resistance of the air against the surface on the inside of the ductwork. And so you can put it through sheet metal, which is nice and smooth. You can put it through rigid duct board with the fiberglass on the inside, and that's not very smooth. And there will be a lot of resistance there. You can put it through flex duct, and that may be nice and smooth, or it may be rough, depending on how it's installed. The flex duct, of course, the inner liner needs to be pulled really tight to make it nice and smooth on the inside. And when you do that, it works almost as well as hard pipe, but that doesn't often happen. The other factor that matters for resistance in the duct system is turbulence. So when you turn the air, when you split the air, when you put things into the airstream like dampers, you build up turbulence in the airflow, and that also slows down the air. So those are pressure drops, things that change the pressure. And a fourth factor that we juggle in the duct design process is the velocity, because the duct size and the velocity go together. A bigger duct is going to have a lower velocity if you don't change anything else. A smaller duct will have a higher velocity. A higher velocity will be noisier. So noise is definitely a consideration sometimes. And so we've got to factor that in. And let's, so of those four factors now, the resistance is the big one. So in Manual D, which is the Air Conditioning Contractors of America protocol for designing duct system, the way we characterize the resistance in a duct system is this thing called total effective length, which has two components: the equivalent length and the total effective length. Now, notice there's two different words there: equivalent length and effective length, but they're used differently. Equivalent length is just for the fittings. That's the resistance in a fitting, and it's the pressure drop in the fitting that's equivalent to the pressure drop in a certain straight length of ductwork. So if you have a fitting and it says the pressure drop, or the equivalent length is 30 feet, that means the pressure drop of the air going through that fitting is equivalent to the pressure drop in 30 feet of straight duct. So that's when you add up all of the equivalent lengths of the fittings to the lengths of the straight ducts, then you get the total effective length. And that number gets calculated into something called the friction rate. We're not going to go into those details, but you've got to get the available static pressure, the total effective length, then you calculate the friction rate, and that tells you whether you have a good duct system or not. So fittings are where the action is at. And so going back to the myth that you can't put too long of a duct system on a low static air handler, it's not the actual length that matters, it's the total effective length. And the fittings determine that way more than the actual length of the duct system. So here's an example of takeoffs from a trunk line. So if you're doing these different kind of takeoffs, you can see that there's a table here, and we don't need to go into all the details of it, but there's different kinds of takeoffs, and where they're positioned on the trunk line has an effect. So if you look through here, you can see, the low end of this is 20 feet. So that one fitting, that one takeoff on the trunk line is 20 feet. Or you could choose a really bad one that's 90 or 95 feet. So that one fitting is equivalent to 90 or 95 feet of straight duct. That's horrible. That's horrible. And here are boots. Boots are the transition piece between a duct run and where the vent is in the room. And again, we've got some that are really low. We've got some 10-foot equivalent lengths here, and we've got a 90-foot. So if you want to do a low static air handler, you've got to pay attention to these numbers, and you want to go for the good fittings. Here's some elbows, and again, it depends on what kind of elbow it is and what the ratio is of the radius of curvature to the diameter of the duct. So those are elbows. So if anybody's getting freaked out, here's a picture of a hummingbird in my backyard. This is a male ruby-throated hummingbird. You can see the nice ruby throat there. I love hummingbirds. I'm tracking the last day that I see them because they migrate. These little guys are amazing. They go all the way down to Mexico and Central America. These tiny little things flapping their wings 1,000 miles a minute, 1,000 beats a second, whatever it is. Anyway, hummingbirds. Let's talk about elbows, because this is where you have a big opportunity to make an improvement. Now, some people looking at this might think, hey, look at that nice radius turn, okay? That's the heel right here. This part is called the heel. So here's some HVAC duct installer terminology for you. The outer part of an elbow is called the heel. The inner part is called the throat. One of those parts is more important than the other. It's not the one that looks nice here. A lot of people are looking at this nice curve, but this is really what determines whether it's a good fitting or not. And here's how you can think about that. Have you ever seen a racetrack, NASCAR, Indy, whatever, where they have sharp 90-degree turns? No, because what would happen, think about the air as race cars going through here. If the air is coming through this way and it's got to make this turn, is it going to just make a sharp 90-degree turn? No, it's going to shoot out this way and then turn, which means this whole area is there's going to be a bunch of turbulence in here. And so this air is going to crash into the air coming down here. So it's a mess. So you don't want a sharp throat. You want a nice radius on the throat like this. This is a house I saw in Toronto, and that looks pretty nice. Here's another one. This is in my house. This is the nice radius throat. It's good to have the radius on the heel too, but when you're looking at elbows, always look at the throat first. That's more important than the heel. So fittings dominate pressure drops, and that's why this myth is not true, because the most of the resistance is coming in the fittings, not in the straight duct. So put in good fittings and do your duct design right, and you can have a low static unit that works perfectly. Poorly installed flex, when we're talking about fittings, usually we're thinking of hard pipe, but sometimes people do everything with flex duct and they turn it and split it with flex duct and everything. So you've got to factor that in. It's hard to know what the equivalent lengths are for some of the stuff they do with flex duct. Like, what's the total effective length of this mess right here? That's hard to know. All right, so let's see. This is the system in our office. So this is a 12K, 1-ton Mitsubishi SEZ unit right up here. The air handler's right up there. We got a transition piece here going to a filter right here. And then we've got a big radius turn right here. And again, there's the throat, nice radius throat with a good radius of curvature relative to the diameter of the duct. So low equivalent length, low pressure drop, radius turn there. And I measured the total external static pressure. That tells you what how good it is. And the system is rated for 0.2. It's running at 0.09. So we're only halfway to the pressure that we could have used. So we've got a really good duct system on this. Now this one is pretty short, and I don't have the schematic for this duct system in the presentation, but it is a fairly short duct system compared to the ones at my house. But and that was that 0.09 inch of water column static pressure was with this airflow. So 363 CFM, cubic feet per minute of air, total airflow, which is about what it's rated for. So we were getting full airflow. This was the pressure drop across the filter, 0.06, so really good. We'll talk about filters some more. I've got another myth coming up, and we'll talk about filters there. So this is one of the air handlers in my house, and you can see the air handler here, the return, the trunk line. So here's the main supply trunk coming out, and it splits, and I've got a picture of that so you can see the nice radius turns there, what I call the pair of pants T. Well, I didn't make up that name. It's been in the industry for a while. But this is a ducted mini split rated for 0.2 inch of water column. And we usually design for lower velocities. The ACA Manual D protocol says, designed for up to 900 feet per minute. If you design for lower velocity, the pressure drops are lower at lower velocity. There's that helps with your duct system. It means bigger ducts, though, to design for lower velocity. It also means if you're not designing for this low velocity, you should make sure that your ducts are in conditioned space or semi-conditioned space. Mine are in an encapsulated attic. If you were putting them into, well, nobody would ever put them into an unconditioned attic, right? Actually, the people who put them in unconditioned attics usually don't do real design, so they're not on this program. So here's what that looks like. So in this diagram, so this part right here is what that next picture is. So here's the air handler, the plenum, and one one part comes out, and this was during installation, so it's not finished yet. So this one's not attached to anything over there, and it's not insulated at this point. But the nice radius throat on both of them, and so we get good even split of the air there, and low static pressure. This was on the return side. You've seen this one before. So works really well. And the static pressure, the total external static pressure on this is 0.13. So a little bit higher than the one at the office, but there's more ductwork here, more fittings. You'd expect it, but still it's rated for 0.2 and we're running at 0.13. Hey, I'll take it. And what I haven't told you yet is that I'm not running with the thin little filters that Mitsubishi sends you. I throw those away with the ducted systems. And I use real MERV 13 high efficiency filters, which gets us to myth number 2. You can't use high MERV filters on low static air handlers. Well, some HVAC people think you can't use high MERV filters on anything. But that's not true. This system at our office, 0.09 inch of water column static pressure, that's with a MERV 13 filter. When I took the filter out, you can see it's at about 0.05. So about 0.04 of the pressure drop was for the filter. 0.04 across the MERV 13 filter. That's pretty darn good. This is my house. This is we got ceiling grills here. They're 2 inches deep. The one at the office is 4 inches deep, and works great. So when I first installed this, I was getting a pressure drop across the filters of 0.08 inch of water column, which is pretty good. ACCA says to put in 0.1 inch of water column for pressure drops across filters. And they're talking about the MERV 2 filters that are usually installed. So I'm getting 0.08 with a MERV 13 filter, but I was not happy with that because here's the problem. Well, I'll get to the problem in a minute. I'll show you how I improved it. But first, how I got to this low of pressure was a simple rule. We, in our design, use 2 square feet of filter area for each 400 CFM of airflow. So 2 square feet per ton, basically. The 400 CFM is nominally a ton of airflow. It's the airflow for 1 ton of capacity. And so the 2 square feet, as I say down here, is just the length times the width of the filter. That does not include all the pleats. It doesn't include the stretched out area of the filter fabric. That's just length times width for the frame of the filter. And that gets us a low pressure drop across the filter. If you're wondering about face velocity, some of you more technical people out there, 2 square feet per ton is about 200 feet per minute of face velocity. And filters are usually tested at about 500 feet of face velocity. Lower velocity through the filter usually means better filtration as well. So another thing. So here's what I was talking about, what I didn't like. So when they first installed the system, I didn't pay attention to this part, but my 2-inch filter goes in this gap up here, which meant this piece of sheet metal was right on the back side of my filter. And the duct goes in, and so a lot of the air was going straight through the middle of the filter and not as much through this part. Although the filter did look uniformly dirty, so some of it was going through the edges, but if I'd left it longer, I probably would have had a nice round circle of dirt in the filter. You need space behind the filter, and ideally you want about 6 inches of space. So I had this retrofitted. So I had this piece of sheet metal taken off, and I had a big box put on the backside. So this is way more than 6 inches. I got about 20 inches, I think. And so 6 inches space. So my pressure drop across the filter went from about 0.08 to about 0.06. So I got about a 30% drop or 30% decrease in my pressure drop just by putting this big box on the back of the filter, giving it more space. What that does, remember earlier I talked about turbulence being one of the factors that hurts your airflow. When you put a lot of space back there, it reduces the amount of turbulence that's happening in the airflow back there. So some other information about filter grills versus cabinet filters. At our office, we have a cabinet filter. At my house, I have filter grills, and cabinet filters, usually close to the air handler. Sometimes, well, as I say, maybe harder to change cabinet filters, especially if the installer does something stupid like run the condensate line right in front of the access panel, so you can't pull the filter out. I've seen plenty of pictures like that. Or worse than the condensate line, because PVC is easy to change, or easier to change than copper. I've also seen copper lines or gas line running right in front of the filter access. So one advantage of the cabinet filters, though, it's easier to get a thicker filter. You can do 4-inch filters on filter grills, but 2-inch filters usually are easier to do for filter grills. Filter grills are in the living space, not in an attic or a crawl space. So they're often easier to get to and check. And they also keep the return ducts clean, because if you put the filter near the air handler, all the ductwork before that filter is running dirty air through it. And dirt will build up in that duct system, in that part of the duct. I mean, is it a big deal? Not really, because as long as you get it filtered out before it goes in and gets redistributed to the house, but it does build up, and it's better to not let it build up, get that on the filter and just get it all out of the house. One thing that you have to do, though, with filter grills is you have to make sure the return duct is super tight, because any leaks in that return duct between the filter and the air handler is going to be sucking in air that doesn't get filtered. So that part, the whole return duct has to be really sealed absolutely tight, so you don't suck in dirt there, because that's under negative pressure. Let's do a little summary here. So total effective length matters more than the total length. So that myth number one is just not true. You can put long duct systems, a lot of duct work on low static air handlers. You just have to pay really close attention to the fittings, because that's where most of the resistance is coming from, and the filters, because the available static pressure that you get is the rated static pressure, like the 0.2, minus the pressure drops of the non-duct items like the filter and dampers and things like that. So you subtract those off first, and the filter is usually the biggest one of those, and then the fittings provide the most resistance in the duct components. So pay attention to those, and you can get a good performance with a low static air handler. The fittings contribute the most, and high-MERV filtration is possible with enough filter area. So these are the three main takeaways. And here's my little monkey on a dog, another cute little monkey, yay. My blog, energyvanguard.com, and I write new articles every week. I have a newsletter. You can sign up for the newsletter and get that once a week. I have links to the new articles. I have a weekly column in there, and that's the end.
Thank you, Allison. That was great.
You're welcome.
If I turn my camera around, you guys would see my shitty duct system that I'm in front of in my basement. This is a green screen, and you would see my not raised heels as my raised heels, but my throats can't get any ductwork, any airflow going through them. So but let's kick it to Shannon and get some questions rolling. Mark,
Oh, absolutely.
Anything to add?
I'm going to throw a couple names in the chat so people have a heads up on who we're going to invite to unmute first. But I want to thank Allison for that presentation, because I learned a lot when we were just hanging out last week, and I learned a ton more tonight. And that was on top of the research I did in between, just to feel like I knew what we were going to be talking about. And I love the transitions that you did between the diagrams and the install photos.
I thought you were talking about the monkey.
Oh, well, of course.
And the hummingbird.
I want to see the monkey on the dog on the Roomba.
Oh.
But really, the transitions between the diagrams and the install photos was very helpful. So thank you for that. And with that, we will kick it off first to Stephen Gibson. Stephen, would you like to unmute and ask your question?
Hey, Allison.
Hey.
Stephen Gibson in Seattle. You can hear me?
I can hear you, yeah.
Awesome. So my first question is, how do you define a low static pressure duct system?
Good question. So the standard for conventional systems is about 0.5 inch of water column. And so anything lower than that. And yeah, in the mini split world, the ducted mini split world, it's usually around 0.2. So they're, somewhere at 0.16, 0.2, 0.12 even, I think I've seen. So those are low static air handlers. 0.5 and higher is the regular world, high static, medium static, whatever you want to call it.
Okay, if I may ask another question, I have an existing air handler burning oil that I'd love to replace with a split system with an air handler that connects to my existing duct system. What is your recommendation around that, knowing that I should design pick a blower before I design a duct system, which is already in place?
Yeah, so in most existing homes, it's often best just to start over with the duct system. If you can't do that, though, it may work. I mean, sometimes in existing homes, the ducts aren't accessible, and that would mean ripping out sheetrock and a huge expense to do something like that. So the best you can do is get a manual J and right size your system. Probably you'll find that the system in your house is oversized. And that's good for using the existing ducts, because the existing ducts are probably undersized for the current system, but they may be sized appropriately for the system that you need, the size system you need. So if you do that, then it may work okay. There's probably still going to be problems with getting the right amount of distribution. If you can put balancing dampers in the system to do some adjustments afterwards, that might help.
Yeah, actually, a lot of the ductwork is exposed in the garage and in the lower level.
Oh, the garage. Oh,
so it wouldn't be the end of the world to replace it. It's just a lot more work.
Yeah. Yeah.
All right. Thank you.
You're welcome.
Thanks,
Allison,
Stephen.
real quick question. What do you consider good duct system air tightness for the duct systems?
Well, if you meet the current code, then that's really good, which is what is it, about 4% duct leakage, something like that.
And it's 4% duct leakage of the total system design flow?
Well, in the codes, they're usually specified in terms of the well, gosh, it's been a while since I thought about that. I know Energy Star specifies it in terms of the floor area. So when I say percent duct leakage, I'm thinking of it in terms of the floor area.
Gotcha.
So 4 CFM 25 per 100 square feet of floor area, conditioned floor area served by that system.
Awesome. Thank you.
Yeah.
Thanks, Allison. I'm going to read the next question from Tom because his mic is not available. And his question, it was Tom Bassett Daly from Oak Park. He said,
Hey, Tom.
Are the good fittings as readily available as lousy ones? Or should we plan on longer lead times and increased HVAC bids? Let's say a component HVAC sub who is accustomed to installing mini splits, not just a couple knuckleheads shopping at Home Depot.
Yeah, great question.
Thank you, Tom.
Great question. So there's a couple things. Some of the fittings are readily available. Some of them aren't. The big radius turns I showed you on my duct system are custom made. So you need a good sheet metal shop for that. And they're used to making stuff like that. So if you have a good sheet metal shop, that's not a big deal. The regular fittings, though, if you can't get the best ones out there, just the main thing is to avoid the worst ones. And if manual D has all these tables of the equivalent length, so just avoid the 60, 70, 80, 90 foot equivalent length fittings. Stick with the 10, 20, 30 foot ones if you can. And the other thing is, and this is what we do in our design, is as much as possible, we try to lay out the duct system to minimize the number of fittings, because for each elbow that you can avoid, that's 20 or 30 feet of equivalent length you have avoided as well.
I hope that answers your question. Thank you, Allison.
Yeah.
Next question is from Aubrey Pure. Aubrey, would you like to unmute and ask your question?
Sure. Hi, Allison.
Hey, Aubrey.
Thanks for a great presentation. I was just hoping that you might talk a little bit about what you think that a good throat radius would be relative to either the diameter or the width of the duct. And related to that, since often bad fittings are used just because of space constraints, can you speak a little bit to using mitered fittings with turning vanes as an alternate when space is tight?
Yes, great question, and thank you for introducing that idea of turning vanes. I didn't talk about that, but yeah, if you can't do the nice radius elbow, an alternative is to put turning vanes in, and these are just little curved pieces of metal that sit in that fitting, and they help the air turn, and they help those race cars make the turn sharper. So turning vanes are a great alternative. And what was the first part of your question, Aubrey?
What do you recommend for radius of the throat?
So let me go back to those manual D equivalent length. So here you can see that 0.751 and 1.5 are the three ratios they give in this table. The bigger the radius of curvature is relative to the diameter of the duct, the lower the equivalent length. So when I was designing the big radius elbow for our office, I used 1. So 1 is kind of the minimum, I would say, that where the radius of curvature is equal to the diameter of the duct.
Right, and in that diagram there, that's the center line radius though, right, Allison, not the throat radius? Right.
Yeah, so this is the radius of curvature. So if you drew a full circle and found the center of the circle to the center of the duct, or I believe it's the center of the duct, then that's what that number is. Yeah.
Thank you so much, Aubrey. Our next question is from Tom Phillips in Davis, California.
Hey, Allison, thanks for the great guidance and all your blogs and everything. I was just asking about the real world performance of filters when they get loaded up in terms of static pressure, because most field studies find that people rarely change their filters. And so the follow-up question is, what would you recommend to incentivize or encourage occupants to routinely check and change their filters? For example, we found in a big field study that the ceiling registers were not changed, especially with older folks, because they couldn't get up on a ladder unless they happened to have a contractor who was kind enough to do it for them when he came in for an annual tune-up or something. So the first question is loading filters. The other one is, how do we get people to change and check their filter?
Yeah, so loading filters do perform worse. They also, it may be MERV 13 when it starts, but as it loads, it's not MERV 13 anymore. It actually gets worse, not better, which is counterintuitive. You'd think it would filter better as it gets loaded, but it doesn't. It actually filters a little worse. One reason for that is most fibrous media filters with the MERV rating have an electrostatic charge on them. They're the electret filters. That's how they get that final push to the rating, the MERV rating they want. And over time, that electrostatic charge dissipates, and that means the MERV rating goes down. So after a few months, your MERV 13 might be a MERV 11 or MERV 10. So I change my filters about every 6 months, and if the filters are sized the way I talked about here, they can go for a year or 2 years without the pressure drop being bad enough to affect the performance. When I changed mine the first time, I think it was 6 months, and I think the pressure drop hardly changed. It was a little bit worse, but not much worse. I have an article about that. I don't remember what the numbers were, but it did get a little bit worse. On the question about changing the filters, so Yeah, I mean, this is, I mean, every HVAC contractor, every HVAC tech will tell you this is one of the biggest problems in most homes is people don't change the filters. And a few years ago, I spent a day going out with an HVAC company on a bunch of calls, and you know, I think we went on five calls, and three of them basically their problem was, you know, one of their problems was the filters were too dirty and needed to be changed. One of them, that was the complete problem. I mean, that was why the system stopped working. So how do you get people to change it? Number one, if they're on a service agreement, and you know, HVAC companies have service agreements that usually aren't that expensive, and they'll come in and they'll check the charge and do all this stuff, and they'll change the filters. Now, you don't, you usually don't need to have all that stuff checked every 6 months in a lot of cases, but you could always just, you know, for the older people who can't get on a ladder to get the ceiling filters changed, they could just hire you know, a grandkid or a kid in the neighborhood or somebody to come in and change it. But yeah, there's all kinds of stuff that people don't do, like flush their water heater, like I did a couple of weeks ago.
Can a monkey do it though?
A monkey, yes. We could train monkeys to do this.
Well, if I were king, I would require everybody to have a service contract and to have air cleaners tested and rated as when they're loaded. So
yep.
Anyway, but thanks for that.
Yeah, no, there is another thing. There's this thing called the filter whistle. I've never tried it, but it's a little plastic whistle that you embed in the filter. And as the filter loads, when the filter is new, most of the air is going through the filter, but as the filter loads, more and more air goes through the whistle, and eventually the whistle starts making a sound, and that alerts the people that, hey, we need to change the filter.
I love that. It's like the
Yeah.
sensor on the brakes, the squeak brakes.
Yeah.
I saw that years ago, but I don't know if it's really been taken up much for whatever reason. But I know for commercial systems, they just put in a pressure gauge, and so the maintenance people can just look at it. And so that might be one way to skin the cat. Of course, now there's sensors that you can do all this and send it to your smartphone.
Yep.
Thank you very much, Tom. We have a question next from Lindsay Klein. Hi, Lindsay.
Remind me, I had two questions. I only wrote down one.
The first was about the MERV 13 filter.
Oh, yes,
Does it
I was
help
fascinated. Yeah.
with
so that-
muffling noise.
Thank you, Shannon. So I was fascinated by this idea of creating a larger filter box at the return air register, or even, and maybe the supply air registers. So would a big filter like that also help muffle the sound from the machine?
That's a good question. It might. I think a bigger, thicker filter would probably muffle more of the blower noise than a MERV 2 1-inch fiberglass filter. But if you're using the kind of air handlers I was talking about tonight, the ducted mini split air handlers, they are very quiet. I can almost never hear my system running.
Well, I had one in a relatively small house, so the ductwork runs are much less extensive than your house, or even half your house. And because it was a passive house, it was so quiet inside. I could hear the refrigerator, and I could hear when there was no one else in the house, I could hear the sound of the air handler. But it was only about maybe 10 feet from the unit. It was a straight run. So suddenly when I saw that image, I thought, wow, I bet that would help.
Yeah, it might help some.
And all the ductwork was lined too, by the way. So it was really just so sensitive.
Yep. And line ductwork also increases the resistance. So you got to account for that in your design.
Thank you.
Now, what Lindsay left out is that one, she has super bionic hearing, and two, your pictures from earlier not only made her feel good, but made all of us feel good about probably what's in our basements and attics and hidden in our walls right now.
Yeah.
All right, our next question is from Jane Sanders. You have two, Jane. You want to come on and ask one of them?
Hi, how you doing? So duct insulation, assuming the ducts are all in the conditioned space, do you always need insulation? And if so, should it go on the outside? Should you use duct liner on the inside? I've had on my passive house projects, on one, we did not insulate the ducts except for the first couple feet after it comes, when it comes out of the air handler. Then another project, it was insulated on the outside. And then on non-passive house projects in New York City, I find that the engineers often spec the duct liner. And I don't like it because I feel like it's going to collect dust over time. And it's like you say, it has friction, but is that mostly done because of sound?
Yeah. Well, it could be done because of sound, but also could be done because of aesthetics. If they're using spiral duct and it's exposed in the living space, but if it's a duct in an attic or a basement or something, that wouldn't be the issue probably. So I prefer the insulation on the outside, and because of what you said, because of the friction, and because yes, it collects dirt and dust. And if you put a humidifier on the system and you're spraying moisture into a duct with a lot of dirt on the inside, you could have a biology experiment going on in there, and that's not good. Your first question though about should you insulate is it okay not to insulate the ducts? And I would say insulate the ducts. I mean, I've got my ducts in an encapsulated attic, conditioned attic, and they are insulated. The return ducts and the supply side are both insulated. The supplies definitely need to be insulated, just in case you end up getting condensation, to prevent condensation, because without insulation on the ducts, there could be times when that air there gets too humid and you get condensation, and that's not good.
Yeah, one problem with doing it on the outside is I find when you're inspecting at the job site, you have to make sure to get there after they seal the ducts, but before they put the insulation on, because often they will insulate and you can't see if they really sealed them properly. And it's too late. Like I've had, everything fully insulated, then you do the duct blaster test, and it's not good. So then you have to open up all that insulation again to find where they didn't seal it properly.
Yep, that's true.
Never fun.
Scare the installers and let them know they're going to be tested. Then they'll make sure it's sealed.
Yeah. Should I do the second question now or wait till later for that one?
Go ahead, Jane.
Okay. So the other one is I've had one project where the engineer designed ducted returns to each room as opposed to the single return in the hallway. And I was wondering what your opinion is on that.
We try to do a central return or multiple central returns instead of ducted returns in each bedroom. We definitely put in we definitely put in return air pathways for each of the bedrooms. But if we, the reason we like to do one or two or maybe three, if it's a big enough system, returns in the main areas, is that those are larger. There's fewer of them, and we can make them all the same size. So the homeowners have to buy only one size filter. They can get a box of one size filter. That's what I did when I got my system put in. I bought a case of 12 filters, and we've got 3 different return filter grills. So that's 2 years worth of filters at every 6 months. So either way is fine. The thing about putting dedicated returns in each bedroom is that you have more ductwork on the return side. You can still make that work, but it's more ductwork and a more complicated duct system.
I appreciate that, everyone. If you can get ready to do a toast in a little bit. And right now, feel free to applause too, right? This is phenomenal. Your hands should be hurting from applauding so much. With the monkey on the dog, I pass the mic over to Zach.
All right. Thank you, Mark, and thank you, Allison. This is great. So I have a few announcements to share. First, I want to thank all of the folks who make the work that we do at the Passive House Accelerator possible. So thank you to our founding sponsors, 475 High Performance Building Supply, Baxtingwe Architects, Glavel Foam Glass Gravel, Minutair All-in-One HVAC and Dehumidification Units, Mitsubishi Electric Train HVAC US, Partel, RDH Building Science, Rockwool North America, Stocorp, and Zola Windows. Our champion sponsors are Icon Windows and Doors and SIGA, and our stakeholder partner is NYSERDA, the New York State Energy Research and Development Authority. Thanks also to our patron sponsors, AeroBarrier, BR+A Consulting Engineers, Brennan Air Tightness and Insulation, Euroline Windows, Inotech Windows and Doors, Lamelux, Sanderson Sustainable Design, and US Engineered Wood T-Stud. Thank you, sponsors. On the podcast, we are featuring our very own Shannon Pendleton. And Shannon talks about her pathway to Passive House. She talks about the interesting history around green building advocacy and practice in Philadelphia, as well as insights around the power of open source architectural information network. So please check out this latest episode of the Passive House podcast. We also have a bunch of bonus episodes going on right now. So these are shorter episodes based on interviews that I conducted during the International Passive House Conference. And the most recent one is with Benjamin Crick, who talks about Passive House and embodied energy and the interesting ways that you need to wrap your head around embodied energy compared to embodied carbon. Really interesting insights from Benjamin. Tomorrow on the Global Passive House Showcase, we have a NYSERDA Buildings of Excellence Round 1 winner project that is called the Rheingold Senior Residence. It's a balanced passive house. So you will join us to find out what that means. We'll be hearing from Sarah Bayer of Magnuson Architecture, and the guest host of tomorrow's episode will be Kristen Graham of NYSERDA. And then on Thursday, please mark your calendars, and I will put a link in chat here for this. This is Rockwool North America's Component Spotlight. This is the first component spotlight we're doing with Rockwool. We're really excited about it. They'll be talking about stone wool solutions for Passive House, drawing from examples, including the Cornell Tech Tower in New York City. So join us on Thursday for that, please. And then just a couple more here real quick. Next week, Construction Tech will be Prefab Experts Hive Mind. So Shannon and others have organized this TheusCon Prefab Panel Sneak Peek. Should be P-E-E-K. So we'll change that. But the speakers, we're going to be kicked off with Katrin Klinenberg, the executive director and co-founder of Theus. And then we'll hear from the panel experts listed here in this cool sneak peek of one of the really exciting panels that will be at the TheusCon conference next week. So that's my final announcement, is that the conference is next week in Tarrytown. So please join us. It's an in-person only conference. There will be videos shared afterward of some of the key sessions, but this, if you want to take this in, you really should be there in person. I'm looking forward to being there. Lots of folks from the accelerator will be there as well. And you can see it's theuscon.org to register. And if you're close enough to make this make sense, you can also register for a single day. So we hope to see you in Tarrytown next week. Thanks.